section we'll look at more methods for approximating the area between the function curve of a function f and the x-axis, okay? What we call trapezoidal and midpoint approximations. So trapezoidal approximation and error, okay? So if we have a trapezoid, which requires a stretch all the way back to geometry, okay? A trapezoid of a width w and height h1 and h2, we know we'll have an area of 1/2 w times h1 plus h2, okay? So this is the area of the trapezoid. The idea behind a trapezoidal approximation is that instead of using rectangles for each subinterval, we're now going to use trapezoids, which if you look, better approximate the area between a curve. It follows the curve more closely over a specific interval. So if we call this x right here, and then we call this next value x plus delta x right here for an individual trapezoid, what we'll take note of is that the height, the leftmost height of our trapezoid is f of x, while the rightmost height is going to be f evaluated at x plus delta x. And then our width between these 2 points is going to be delta x. So the area of a trapezoid then, where we're looking at the kth trapezoid, okay, is going to be 1/2 delta x, our width now, we replace w with delta x, times f of x sub k. F of x sub k now is our height h1, plus f of x sub k plus delta x, the function value of f evaluated at x sub k plus delta x, which is h2. All right, so this forms the basis for how we get our area for the kth trapezoid in the trapezoidal approximation. So the basic steps that we're going to follow is, again, we're going to determine delta x for n subintervals, or again, n trapezoids, okay, where delta x, again, is b minus a divided by n. In a table, we're going to determine the x-coordinates to be used, starting at x equals a and incrementing by delta x. Again, so it's the same, these first two techniques are exactly, or first two steps are exactly the same steps that we used for last techniques in 4.1. And then in the same table, we're going to calculate corresponding values of f at each x-coordinate, okay? So these first three steps are all the same. So it's nothing new, so it's nothing extremely novel, okay? And then the fourth step is the same thing. We're going to calculate the area of each subinterval and add together areas, except now we're going to have to use, okay, the area formula that we calculated out, or we derived in the last slide, okay? So notice that the points interior of A and B will be used twice since they form the boundaries for each trapezoid. So if this is our first trapezoid right here, okay, f of 1, all right, is going to be used for the rightmost height of this first trapezoid, but then when we get to the second trapezoid, f of 1 is going to be used as the height for the leftmost height of our trapezoid. Okay, so the interior points on our interval will be used twice since they form boundaries for each trapezoid. So trapezoid approximation error. All right, so if we look at errors for trapezoidal approximations, what we need to look at is the concavity of our function. Okay. So specifically, we see that if we're concave down right here, all right, we see that our trapezoid is going to fit beneath our curve, and thus the area calculated by the trapezoid is going to be less than the actual area of our curve, the actual definite integral. While if our function is concave up, we see a trapezoid is going to exceed and lie above our curve, and thus the area of the trapezoidal approximation will exceed the actual area between the curve and the x-axis, so it will be greater than the definite integral that we're calculating. So as a result, if f del prime of x of our second derivative is less than 0 over an interval, then the trapezoidal approximation will be less than the actual value of the area slash definite integral, again because the second derivative being less than 0 tells us we're concave down. And on the flip side, if we're concave up, meaning our second derivative is greater than 0 over an interval, then the trapezoidal approximation will be greater than the actual value of the area. Okay, so these are things that you can remember and memorize if you would like, but if you ever get stuck, you can visualize this by drawing out what this would look like on a test and then relating that back to the conditions with concavity. So now we're going to move on to the midpoint approximation. So the midpoint approximation, all right, The first step is the same as before. We determine delta x for n subintervals, okay? Except now the idea behind a midpoint approximation is instead of using a left endpoint or right endpoint, we seek a compromise where we use the midpoint between the left and right endpoints for a subinterval to calculate our height, okay? So in a table, what we're going to do is we're going to determine our first midpoint, which is going to be a plus 1/2 of delta x, okay? Again, we start off at a, delta x takes us to x1, but we want to go in between a and x1, so we take half of delta x, okay? Then, in order to get the remaining midpoints, okay, let's say we go from the midpoint of a and x sub 1 to the midpoint between x sub 1 and x2, we're going to be incrementing by delta x. So as a result, we're going to increment by delta x each time to produce the other midpoints. Okay, so once we found our first midpoint, a plus 1/2 delta x, we increment by delta x to produce the other midpoints. Excuse me. So now once we have that table set up, we use the midpoint of each subinterval to determine f of x for that subinterval, aka the height for that subinterval. And then we determine the area of each rectangle as we have done before, and we add all those areas together. All right, so again, one point to illustrate is that the distance between each midpoint is delta x, since delta x represents the distance between identical points in each subinterval. So if x sub 1 star is the midpoint of our first rectangle and x sub 2 star is the midpoint of our second rectangle, okay, the difference between these two is going to be delta x. Since they represent identical types of points, the midpoints for each rectangle. Now, there is no specific error approximation technique for midpoints in stark contrast to the other techniques that we used for our left and right approximations or trapezoidal approximations. So let's take a look at an example problem here. A trapezoidal approximation with 4 subintervals of equal width. Okay, we're looking to evaluate the same function as we've done before, x cubed, where the integrand is x cubed from x equals 1 to x equals 5. We're going to look to do that using a trapezoidal approximation of 4 subintervals of equal width. Determine if the approximation is less than or greater than the actual value of the definite integral. So we start off the same as before. We calculate out delta x. Okay, delta x equals 1 in this case. It's the same problem as from the 4.1 slides. Okay, so we're going to have x equals 1, 2, 3, 4, and 5. Okay. And then we're going to have the same y values, same function values. F of 1 is 1, f of 2 is 8, f of 3 is 27, f of 4 is 64, and then f of 5 is 25. Okay, or excuse me, 125. So now when we come to approximating our integral here, we're going to have 1/2 of delta x times f of 1 plus f of 2, plus 1/2 of delta x f of 2 plus f of 3, plus 1/2 delta x f of 3 plus f of 4, plus 1/2 delta x f of 4 plus f of 5. Note that in this case right here, all right, delta x, 1/2 delta x is the same for each term, so we can factor out 1/2 delta x in this next step to get 1/2 delta x times f of 1 plus 2 f of 2 plus 2 f of 3 plus 2 f of 4 plus f of 5. If you're wondering where the 2 f of 2 comes from, the 2 times f of 2 and the 2 times f of 3 and the 2 times f of 4, all right, recall that each interior point, function value is used twice. So we see we have f of 2 right here being used 2 times, we have f of 3 being used 2 times, and we have f of 4 being used 2 times. So we can condense that down by writing 2 times f of 2, 2 times f of 3, and 2 times f of 4. So as a result, we're going to get 1/2 times 1 times 1 plus 2 times 8 plus 2 times 27 plus 2 times 64 plus 125, which gives us roughly 162. If you recall from last video, our area actually turned out to be 100 using a left endpoint, and I believe 225 using a right endpoint. So we actually get something between 106 between those two, specifically 162, telling us we're on the right track. So in order to evaluate our area, we need to determine a second derivative to determine concavity. So for f of x equals x cubed, the second derivative is going to be equal to 6x. So we're going to have an inflection point when 6x equals 0 or x equals 0. All right. If we evaluate our second derivative to the left of x equals 0, we're going to get something negative. And then if we evaluate f of x, or our second derivative to the right of x equals 0, we're going to get a positive value for a second derivative. So that indicates to us on the interval from x equals 1 to x equals 5, our second derivative is positive, and hence we're concave up. So as a result, since we're concave up, all right, that means that 162 is going to be an over approximation, meaning that our actual area, our actual definite integral, is going to be less than 162, our approximate area using the trapezoidal approximation. Lastly, we use a midpoint approximation, okay? So we use a midpoint approximation of 4 subintervals of equal width to determine our integral here. So again, the first step is the same, delta x equals 1, okay? Number 2, our first midpoint is going to be 1, all right, plus 1/2 of delta x. So we start off at, remember that our starting point is x equals 1. So to get our first midpoint, we're going to increment by 1/2 of delta x, which is 1/2 of 1. So we're going to get that delta x, or excuse me, our first midpoint is 3 over 2, okay? So as a result, we're going to get 3 over 2 for our first midpoint. For a second midpoint, we're going to get 5 over 2, and for 7 over 2, and then we're going to get 7 over 2 for our third midpoint, and then 9 over 2 for our fourth midpoint. We're not going to go to 11 over 2 because 11 over 2 is 5.5, which is outside of our interval of interest here. So now if we evaluate the function values at these specific midpoints, we're going to get f of 3 over 2 is 27 over 8, f of 5 over 2 is 125 over 8, f of 7 over 2 is 343 over 8, and f of 9 over 2 is 729 over 8. So evaluating out this integral is going to give us f of 3 over 2, or excuse me, evaluating this integral now is going to give us the area of the first rectangle is f of 3 over 2 times 1, plus f of 5 over 2 times 1, the area of the second integral, f of 7 over 2 times 1, the area of the third integral, plus f of 9 over 2 times 1, which gives us our area of the fourth rectangle. Okay? So as a result, we're going to have 27 over 8 plus 125 over 8 plus 343 over 8 plus 729 over 8, which gives us 153 for our approximate area of the integral. And these are approximation techniques for evaluating the definite integral of a function over a specific interval.